In this lab, we'll be exploring how to use Pulse Width Modulation, or PWM, to control the brightness of an LED on the RGB module connected to your Raspberry Pi. We'll be focusing on the red LED for this lesson, and we'll use GPIO pin 17 with a frequency of 500 Hz. The demo code for this project can be found in Lab 4, Demo Code, Red RGB PWM.py. Make sure you have this file ready as we go through the steps together. Before we dive into the code, make sure your RGB module is properly connected to the Raspberry Pi. If you haven't set up your RGB module yet, please refer to the previous lesson for a detailed guide. Once you've got everything connected, we can move on. Now, let's take a look at the Python code we'll be using to control the red LED. We'll break it down step by step so you can understand how it works. At the start of our code, we define constants. A constant in programming is a value that doesn't change during the execution of the program. By defining these values as constants at the top of the code, we can easily reference them throughout the program without needing to retype or remember the specific numbers. In Python, it's a common convention to write constants in all capital letters so that it's clear they are not meant to be changed. This makes the code easier to read and understand for anybody reviewing it later. Here's what each constant represents. Red _ pin represents GPIO 17, which is the pin controlling the red LED. Frequency is set to 500 Hz, meaning the LED will pulse 500 times per second. Duty cycle is 50%, meaning the LED will be on for half of each cycle, controlling the brightness. Next, we need to configure the GPIO pins on the Raspberry Pi and initialize the red LED in the off state. Here we're using BCM pin numbering, which refers to the Broadcom chip-specific numbering. GPIO 17 is set as an output pin. Now you might be wondering why we set the pin to high to turn the LED off. That's because of how the RGB module is wired. The LEDs on this module are always connected to the positive voltage 3.3 volts through their VCC pin. What we control is the connection to ground. When the GPIO pin is set to high, there's no difference in voltage between the pin and the positive side, so no current flows, and the LED stays off. On the other hand, when the GPIO pin is set to low, the circuit is complete. The current flows through the LED, turning it on. So setting the pin to high here ensures the LED is initially off. Now that the GPIO pins are set up, we can create a PWM object for the red LED. This line of code initializes the PWM on GPIO 17 using the frequency we defined earlier at 500 Hz. The PWM object allows us to control the brightness of the LED by adjusting how much time during each cycle the LED is on versus off. This is controlled by the duty cycle. In our case, we've set the frequency to 500 Hz, which means the signal will repeat 500 times per second. When we start the PWM, we will specify how much of that cycle the LED will be on. To light up the red LED at half brightness, we start the PWM with a 50% duty cycle. The start method begins the PWM signal, with the duty cycle determining how long the LED stays on during each cycle. In this case, we've set the duty cycle to 50%, meaning the LED will be on for half of the time and off for half of the time. This results in the LED appearing dimmer than when it's fully on because it's only receiving power for part of each cycle. The program is running inside an infinite loop, meaning it will keep executing until we manually stop it. Here the code manages that. This part of the code runs in an infinite loop using while true. and the time.sleep1 ensures that the program pauses for 1 second between each loop iteration. Although PWM is constantly running in the background, the time.sleep1 here makes sure that the loop doesn't execute too rapidly. Without this delay, the loop would run as fast as the processor allows, which could unnecessarily consume CPU resources. The 1 second pause provides a controlled and steady execution without affecting the PWM signal that keeps the LED pulsing at 500 Hz. To stop the program, you can press Ctrl+C, which triggers a keyboard interrupt. When the interrupt occurs, the accept block is executed, stopping the PWM and calling GPIO Cleanup. Once the program is done or interrupted, it's important to clean up the GPIO resources to avoid issues with future programs. This command resets all the GPIO pins that were used in the program to their default state. Without this cleanup, the GPIO pins may remain in the previous configuration, which would interfere with future scripts that need to control the same pins. For example, if the program leaves a pin set to output or PWM mode and doesn't clean up properly, it could lead to unexpected behavior in the next script. Calling GPIO.cleanup ensures that all the pins are properly reset, so you can start fresh the next time you run a program. Now that we've walked through the code, it's time to see it in action. Open VS Code and navigate to the script file. Once you've opened the file, click the Run button, and you should see the red LED on your RGB module light up at half brightness. The program will keep running until you manually stop it. In this lab, we demonstrated how PWM allows us to control the brightness of an LED. In future labs, we'll explore controlling the green and blue LEDs, even creating more complex light patterns. Feel free to experiment with different duty cycles to see how it changes the brightness.